So let's do a great job. I'm going to do a great job teaching because I am prepared. 31617. Common Core Standard is F for functions, I for interpreting functions, and it is part E, and it's using logarithms. And exponential functions to solve problems. Okay, and today we'll do the exponential ones, and tomorrow we'll talk about the logarithm functions, all right? So let's take a look. At number one, example one, a bacteria colony doubles every 3 hours. So I'm thinking, okay, I've got some formulas that I wrote down in my reading, and I'm going to use my doubling formula, okay? I want to use that one right there. So I'm just going to write it down for right now. It's like n of t, which is the number after time. That's the n stands. The number of bacteria over time is equal to, well, it's our n0, which is our starting number, times 2 to the t over big T, okay? Now, let's see what we can do. So my initial population is 1,000. That's my initial population, so I'll put 1,000 right there. And we are doubling, so I'll keep the 2. So we'll go 1,000 times 2. And now what we're going to do is it doubles every 3 hours, so my big T is 3, okay? So it says find an equation. So I'm going to have this n of t, and I'm going to leave little t as little t because that way we can let time be any time. We can have an experiment. So my equation is going to be this n of t, or the number, that's an n by the way, this is the number over time, is equal to 1,000 times 2 to the t over 3. Okay, so real quick I'll back up. N of t is the number, the amount over time. There's my initial, my starting population. I am doubling, so I use the 2. Little t is the time, so we can let this experiment run as many hours as we want, but we do know that every 3 hours they double, okay? So B, how many bacteria will there be when after 15 hours? So just plug 15 in for t, right? So n of 15, which is the number after 15 years, right, is equal to my 1,000, 2 to the 15 over 3. And I'm going to use my calculator, right? So I know 15 over 3 is 5, right? So I'm just going to use 5 there. So I'm just going to take my calculator, and I'm going to go 1,000 times 2 to the power of, how about 5, right? How about 5? So 15 over 3, how about just 5, right? And I get 32,000. So that's a lot of bacteria, right? 32,000 cells, I guess. We'll call them cells. I don't know if they're cells, but they're bacteria. They're bad, okay? So far, so good? Is that pretty easy?
Yes.
Okay. Now, C. When will the population equal 100,000? Now, when? Now, when? We're going to have to look for time, right? So we want this to be our ending amount. So we're going to set it equal. So we're going to go 100,000 equals our 1,000 times 2 to the t over 3. So this time we have to solve for the time. We say, how much time does it take for 1,000 to become 10,000, okay? Because if it doubles over 3 hours, how much time is that going to take? Well, I got a problem. If I have a variable in the exponent, I'm going to use logs. I will. I'm going to have to use a log, but not quite yet. First step, let's just divide by 1,000, okay? So let's divide by 1,000, divide by 1,000. I'll cancel some zeros, right? So I'll really have a 100 equals a 2 to the t over 3, right? And now I'm going to have to take the log of both sides. If you want to float that exponent down, you've got to log both sides. So I'm going to go log 100 equals, and I'll float it out. I'm going to skip a step, but you guys know what I'm doing. I'll float it down and have a t over 3 log of 2, right? I'll divide by log 2, divide by log 2, right? I already, log of 100, by the way, is 2, but that's okay. So I'll divide by log of 2, and I'll have t over 3 equals whatever log 1,000 is divided by 2. Okay, so then I'll just use my calculator. I'm going to go log 100 divided by log 2, and I get an answer. Oops, that's not right. Forgot to divide. One more time. Log of 100 divided by log 2, and I get about a 6.64, right? 6.64, and the last step would just be to multiply by 3, right? So multiply by 3 times this by 3, and I get an answer about 19.9, or about 20 hours, right? Approximately 20. So it'll take about 20 hours for it to go from 1,000 cells to 100,000. So they're doubling, and of course we looked at that whole problem when, we talked about having mom or dad pay us a penny a day and doubling and doubling. It gets big fast, right? Okay, now let's sketch this graph. Now there's two ways to sketch the graph. One, we could put it in the calculator, okay? But I have enough information here that I can do it by hand. Now it doesn't have to be perfect, but I know this. I know the shape, okay? What shape am I going to draw? I know the shape of it. What kind of shape is this graph going to look like? Yeah, it's going to curve up. It's growth, right? So I know for sure if I were to graph this, I'll sketch the graph over here on the side because I'm running out of room. But I'll do my axes like this. And I know some important things. I know that it started at 1,000. So if I make this be 1,000, right? And I know at 15 hours we're at 32,000, right? So maybe I can go 5, 10, 15, 20, 25, right? And I may have to change my axes on my y. I may have to make this, well, I got to get to 32. So it'll be 10,000, 20,000, 30,000, and I'm never going to be able to reach all the way up to 100,000. So I'm going to have to estimate 1,000. 1,000 might be there. You guys okay with that? Beginning amount, 1,000. I know at 15 hours I'm at 32, so I can put a dot right here, okay? Now we're going to just draw it in so it curves up. Does that make sense? So don't draw it straight because we know it's exponential. So I'm just going to try and do my best to make it look kind of curvy. So I'm just going to draw in something like this. How's that? So I really only put down 2 points, didn't I? But I knew the shape of the curve, so 2 points was enough. Just curve it up, right? Exponential growth, right? Okay. Number 2. Plutonium. No, it's polonium. Polonium-210 has a half-life of 140 days. It's pretty radioactive stuff. It's going to disintegrate pretty quickly. Okay, half of it will be gone in 140 days. It's the kind of stuff they make in labs because it's dangerous. Okay, so the scientist has 300 grams of the sample. Okay, so B, find M of T that models this after 2 days. So I'll go to my half-life formula. Right, I'm going to use this one right here. Okay, so I'm going to use my M of T equals my M0 1/2 to the T over the big T, okay? So to make an equation, all right, I'm going to go M of T equals, all right? Am I going too fast? Let you catch up for a second. Okay, I'm going to use this formula, and I'm just going to plug in the things I know. So I know the beginning amount is 300, 1/2, T. Now I need it in terms of T, right? So I leave T as T, and the cycle of the time is the 140 days. Every 140 days you lose half, so just put 140 here, okay? This is not that hard, is it? It's pretty easy, I agree. Okay, now, yeah.
Why did you put M and then 0?
Oh, that. So this represents the mass at 0 time, which we call initial, okay? That little 0 means what was the mass when time was 0?
Okay,
so
does it ever change?
No.
Okay.
It's always the beginning amount. Whatever goes here is always the beginning amount, right?
So
Yeah, and so when you see this, it's just initial, starting time at time 0, okay? Good question. So now, there's my formula, right? C, find the mass remaining after 1 year. Well, 1 year, this is in terms of days, right? Let's let T equal 365, right? Because this is in terms of days. So my equation's in terms of days, so let's put 365 right in here. All right, so I'm going to go m of t equals my 300 times 1/2 to the 365 over 140, okay? And I'm going to use my calculator, but I'm going to be careful in my calculator. I'm going to make sure I use parentheses for the exponent, so both those numbers go in the exponent, so that makes sense with my calculator. I need both those numbers in the exponent, so I'm going to have to use parentheses so that it goes in my calculator like that. So here we go. Let's just go ahead and take my 300 parentheses 1/2. So you just put the 1/2 like that to the power of, and I'm going to go parentheses 365 divided by 140. Okay, right? So I've got my 300 times 1/2 to the power of, and I use the parentheses because both these numbers need to be my exponent. I get about 49.2. Okay, so about 49.2 grams are left. Okay, not too bad. Okay, D. What are we going to do about D? Well, with D, how long will it take, that's in time, so we're going for time, for the mass to decay to 200. So we're going to set it equal to 200. So this is my ending mass. We're going to go 200 equals, well, let's put my formula in, right? 200 is equal to my 300 times my 1/2 to the t over 140. Okay, I've got to solve for t. T is in the exponent. I'm going to have to log. Eventually I'm going to have to take a logarithm, right? Let's divide, though, first by 300, right? Divide by 300, divide by 300, and I get 2/3 equals a 1/2 t over 140, right? Okay, let's bring that exponent down. What are we going to do? Yeah, let's take the log of it. So we'll take the log of 2/3 equals t over 140 times the log of 1/2, right? And I skipped a step, but you guys know what I did. I brought that down because I took the log of it, right? Okay, so I got to solve for t, so let's divide by log of 1/2. Divide by log of 1/2, right? So I'm going to divide by log 1/2. And I'm just going to use my calculator to find out what that is, so clear. I go log of 2/3, close the parentheses, divided by log of 1/2, right? You're going to answer about 0.5849 blah 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 equals t over 140, right? Multiply by 140. Multiply by 140 times that answer by 140. And I get about 81.9, or pretty close to just about 82, okay? So about 82 days. Not bad, right? Thumbs up. So as long as the formulas are given to us, all we have to do is plug things in and solve, right? Okay. Okay, return. Right. So, example 3. So I get this cup of coffee, right? So I get a cup of coffee, right? And what I know is this, that, sure, I've got a cup of coffee, and the initial temperature is 200 degrees. Just came right out of the microwave. It is hot, right? If you were to drink this coffee right now, it'd burn your tongue. So, since we're all pretty smart about it, we set it aside, right? Or we put an ice cube in it, right? One or the other. Okay, yeah.
Can you only heat it up to 180?
In a microwave?
No.
Well, you can,
At Starbucks.
oh, I don't know.
You can only get it to 180.
Probably. I know if I put it in the microwave, though, I can get it hot, right?
Maybe.
Yeah. So let's say I pull it out of the microwave, right? Or I got drip coffee and I take it off the kettle and it's boiling and I pour it in the cup, right? It's hot, right? Yeah, it's hot.
They can only get it to 140.
So the outside temperature is 70 degrees, right? Outside, right? And then after 10 minutes, so T equals 10, it's going to cool down. It's going to cool down to 150 degrees, okay? Okay, so what we want to do is find an equation, okay? So let's go ahead. So we've got this coffee, I call it the coffee formula, but it's this law of cooling, okay? We're going to use this one right here, okay? The law of cooling, because the coffee's cooling out. So we're going to use this one right here. So let me write that down. I've got my T of S, I'm right up above here, my T of little t equals TS plus D0, that's my initial, right?
TS?
Yeah, temperature, surrounding temperature, yeah. E to the negative K over T, all right? Now, what do I know? Well, I know a few things. I know that I can start right off. I know this right here is going to be 70, right? That's going to be 70. That's my surrounding temperature. And then this D0 here is equal to the coffee temperature minus the room temperature, okay? It's the difference between the two, okay? So this D0 is my coffee temperature minus my room temperature, so it turns out to be 130, okay? And the reason that's an important one is because obviously, you know, the colder it is outside, right, then the faster it'll cool down, right? So let's see what we got. We've got a T of T equals my 70 plus my 130 e to the negative k T. I don't know T. I don't know. Actually, I don't know K. It'd be really nice if I knew the K. But you know, how many people realistically know the cooling constant for every cup? I mean, there's a special number for every cup, right? Nobody knows that, but we can find it out for this cup, right? I mean, do they manufacture? Oh, by the way, the cooling constant in this thing is like negative 0.003. No, of course not. But we can find it. How do we find this value K? Well, we know in this case T is going to be 10, right? And when it's 10, the temperature cooled down to 150. So let's say 150. After 10 minutes, it cooled down to 150. It's equal to 70 plus 130 e to the negative k times 10. So I need to find the rating. Let's call it the rating of my cup, right? How well insulated is my cup? I don't know. I need to find what the rating of this cup is by solving for k. All right. Looks like we've got a variable in the exponent, which means we'll probably have to take a logarithm, right? But let's solve first, okay? Minus 70 gives me, what's that, an 80? Equals 130 e to the negative k times 10. Divide by 130, divide by 130. What's 80 divided by 130? I don't know. 80 divided by 130. It is about a 0.6. Now I'm going to leave this in my calculator for accuracy. So it's about a, I'm going to scoot over here, about a 0.615, we'll say 4 equals my e to the negative 10k. I just switched those around, okay? All right, let's get that thing down. Let's get this exponent down. How are we going to do it?
Natural log.
Yes, we're going to log it, but let's specifically use a natural log. You guys agree with that? Okay, so let's do the ln. So we'll do ln of 0.6154 equals ln of this, which gives me negative 10k, ln of e, but that just disappears. Okay, you guys all right with that? ln of e just disappears. And now I'll just divide by negative 10. So my calculator, the value of the k, and I'm going to use my calculator. So I'm just going to go my natural log of that answer divided by negative 10. And there it is. K is about 0.04855. Okay, so for accuracy, 0.04855. That would be the rating of my cup. And of course, cups aren't manufactured with a rating. Who cares, right?
Is that a good rating?
You know, I don't know. That's a really good question, actually. Lane, you ask good questions. I don't know. I need to do a little bit of homework, don't I?
Is that like the Hydro Flask or?
It's a great... No, it's a very good question. That's something I should look up, right? I like that question.
We should see like what a regular cup is.
I know. I think that's a great... Let me do a little looking up tonight, and I'll see, okay? Or maybe you do. Nah, you know, that's okay. You do it. Okay. Well, let me finish the problem, okay? So, here's my equation. Let's make an equation. So, my equation is going to be, you ready? My equation is going to be T of S equals 70 plus 130 e to the negative 0.04855 t. There's my equation. Can you guys see it? Okay. So I put, here's my 70 plus my 130 e to the negative 0.04855 t. Okay. Now I've got my equation. Now I can use my equation. So in B, let's use my equation. Okay. So it says, what's the temperature after 15 minutes? Let's just plug 15 in. So we're going to go T of 15 equals 70 plus 130 e to the negative 0.04855 times 15, okay? So this should tell me what the temperature of the coffee is after 15 minutes. So I'm just going to use my calculator. I'm going to go, all right, 70 plus 130 e, right, to the negative 0.0488, nope, not 88, 855 times 15, right? See what I got in my calculator? Boom, about 132 degrees. I think I could probably drink coffee that's 132 degrees. So it's about 132.7 degrees, okay? So if we sit it out for 15 minutes, we come back to it, we could drink it, right? It won't burn my mouth. So C, how long will it take? Now we're going to have to find T. How long will it take to cool down to 100 degrees, right? So maybe it's for a baby. We can't give the baby their milk until it's down to 100 degrees, right? And being a good mom or a good dad, we're not going to put scalding hot baby milk into a baby's mouth, right? So let's set it equal to 100, and we'll do our 70 plus our 130 e to the negative 0.04855 t, all right? Let's solve. Okay, so what do you think we got to do first? Minus 70, so I got 30 equals 130 e to the negative 0.04855 t. Good. What should I do next? Divide, right? So 30 divided by 130 is going to be an ugly decimal, so that 0.2307 equals e to the negative 0.04855 t. I got to get the exponent down, so what am I going to do? Got to bring it down. What am I going to do? We're going to log it, right? ln's better. We're going to natural log it, so we take the ln of 0.2307 is equal to negative 0.04855 t, because the ln of e just cancels, right? I just divide now, right? So let's see what t is equal to. All right, ln, that answer divided by negative 0.0855, and I get an answer about 17.1, and that'd be in terms of minutes, right?
Was that a little scribbly thing? E?
Yeah, I crossed out the e.
Okay, so no E?
Yeah, what I did, and I skipped a step, is I just took the natural on both sides. So when I take the ln of both sides, right, the ln of e just cancels out, right? So you just cancel it out, right? Yeah. Now, let's graph it. Again, we don't have, well, you could put it in the calculator, you can look at it, but I have enough information, okay? So, make a little graph. I've got time here, so I'll go probably 5, 10, 15, 20, right? I've got temperature, so we know it started at 200 degrees, so I'll go 200, I'll put 100 here, right? That's 150, right? So I know it's going to go down because it's cooling, right? And it is exponential, so it's going to be curvy, right? It's got a curve. It's got a curve down. So we don't need a calculator if we're just smart about this, all right? So at time 0, we're at 200. So I'm going to put a point at 200, right? I also know at 15 minutes, it was at 132. So I can guesstimate 132, guesstimate, right? So right about there, right? I also know it was 100 degrees after 17 minutes. So that's about 17 and about 100. And then I can just go like this. How's that? Now, it's just a real obvious thing. I did not graph this side of the graph. I didn't put any date over here.
Because you can't go higher than that temperature.
That's fine.
Both. I'm not going to go back in time because I'm pulling my cup out, right? So as soon as I put the cup in, it was never hotter, was it? It was never hotter. It was at its hottest and I pulled it out, right? And that's why I start there. And that would be negative time, but negative time it was heating up, right? Okay, so there's not that many problems. And they all use these formulas, okay?